Prior to our break, we discussed the 8 basic addressing modes. Now we're going to cover 4 special addressing modes involving just the program counter. As we've already seen, General Purpose Register R7 functions as our program counter, or PC. This PC is unique from our other GPRs in one respect. Whenever the processor fetches an instruction from memory, it automatically advances the PC by 2. As a result, the PC points to the next word in the program. This action occurs independent of the addressing mode chosen. We can combine this automatic advancement of the PC with 4 of our basic addressing modes to produce 4 special PC modes. These special PC modes are called immediate, absolute, relative, and relative deferred. As we'll see later on, these PC modes can provide special advantages when we're handling certain kinds of data. By the way, although these modes are given special names, they're still equivalent to our basic addressing modes. The only difference is that the PC is selected in place of the other general purpose registers. Now, let's begin our discussion of the 4 special PC modes by first looking at the immediate mode. In this example, the PC contains the address of the next instruction to be executed. This instruction happens to call for mode 2, which is the auto-increment mode. The instruction also stipulates that mode 2 is to be used in combination with register 7, our PC. While this instruction is being fetched, the PC is automatically updated by 2. This action occurs independent of the auto-increment mode. The new value in the PC is the address of our operand. In other words, when PC mode 2 is called for, the operand appears in the word location immediately following the instruction. Remember, our instruction called for the auto-increment mode. Consequently, when the instruction is decoded, it causes the PC to be auto-incremented by 2. In this example, the new value, PC plus 4, addresses the next instruction in the program. Thus, the PC is incremented twice when it's used in conjunction with addressing mode 2. The first time it's incremented, the PC points to the operand. The second time it's incremented, the PC points to the next instruction. This special PC addressing mode is referred to as the immediate mode, since the operand immediately follows the instruction. Later on, when we cover PDP-11 programming, you'll find that the immediate mode is very useful for working with frequently used constants. For example, to increment the value 100, we could write the increment instruction as shown here. The symbol preceding the value of 100 designates that we're using the immediate mode. In other words, the operand to be incremented, in this case 100, is stored in the first word location following the instruction. That wraps up our discussion of the immediate mode. Now, let's take a look at another one of our special PC addressing modes, the absolute mode. This instruction calls for the absolute mode. In other words, it indicates that addressing mode 3 is to be used in conjunction with register 7, which is our PC. When this instruction is retrieved from memory, the processor automatically advances the PC so that it now points to the next location in the program. What does this location contain? Well, to find out, let's go back to our basic addressing modes for just a moment. As we noted earlier, whenever an instruction calls for addressing mode 3, the selected GPR contains a pointer. This pointer directs the processor to a memory location that contains an address. When this address is retrieved, it directs the processor to the desired operand. Thus, if addressing mode 3 is used, the GPR points to the address of an operand. In this case, the GPR happens to be our PC. Therefore, when an instruction specifies the absolute addressing mode, or mode 3, the updated PC points to the address of an operand. Remember, this address appears in the first word location following the instruction. Once our instruction is decoded, addressing mode 3 causes the processor to auto-increment its PC. The new value, PC plus 4, directs the processor to the next instruction in the program. Consequently, when an instruction calls for the absolute addressing mode, the PC is actually incremented twice. The first time it's incremented, the PC points to a memory location containing the address of an operand. Then, the PC is auto-incremented in response to addressing mode 3. The new value appearing in the PC directs the processor to the next instruction in the program. Remember that the absolute addressing mode, shown here, is nothing more than an auto-increment deferred mode using the PC. We use this notation whenever we're calling for the absolute mode to address an operand. In this example, we intend to increment the operand stored in memory location 1000. Note that this memory location, or address, is written as part of our increment instruction. The two symbols following the opcode, INC, indicate that the number 1000 is to be interpreted as the absolute address of the operand. Now let's see how this increment instruction is stored in memory. Because this instruction calls for the absolute mode, it actually requires two word locations instead of just a single location. The opcode, addressing mode, and register fields occupy one word location. The operand's absolute address of 1000 then forms the second word of this two-word instruction. Why do we refer to the address as an absolute address? We call this the absolute address because the location of the operand remains constant no matter where our instruction is stored. Here, the increment instruction is initially stored in memory locations 600 and 602. Notice where the operand is located with respect to this two-word instruction. Now, we've moved this instruction to memory location 1500 and 1502. Notice that the location of our operand has not changed. The operand is still stored in memory location 1000. In other words, the address of our operand does not depend on where the instruction is stored in memory. The operand's address is absolute. Hence, we call this the absolute addressing mode. We've now covered two of the four special PC modes. Now, let's go on to the relative addressing mode. The relative addressing mode is the same as index mode 6, except that it's used in combination with the program counter, or PC. Let's take a minute or so to review the function of the index mode. Recall that when we use the index mode, the address of an operand is calculated from two components. One of these address components is referred to as our base. The other is called the index. By summing the base with the index, we produce the effective address of an operand. Do you recall where we placed these two address components? Well, the base is stored in any one of our general purpose registers. Since the PC is a general purpose register, its contents can be used as our base. Our other address component, the index, is then stored in the first word location following the instruction. Thus, to obtain the effective address of an operand, we take the base value stored in a GPR and add it to the index word that follows the current instruction. Now that we've reviewed index mode 6, let's see how it relates to our relative addressing mode. This instruction calls for the relative addressing mode. In other words, it specifies index mode 6 is to be used in combination with the PC. Let's see what happens when this instruction is retrieved from memory location 600. As our instruction is being retrieved, the processor automatically updates its PC. The updated PC now directs the processor to memory location 602. Since the instruction has called for mode 6, memory location 602 contains an index word. While this index word is being retrieved, the PC is updated again, this time to 604. The value 604 represents the address of the next instruction in the program. The value 604, which appears in the updated PC, is also treated as our base. This base is added to the index word retrieved from memory location 602. The sum represents the effective address of our operand. Hence, we've located our operand by adding an index value, or offset, to the updated contents of the PC. This is referred to as the relative addressing mode. Remember this important point. With relative addressing, the location of our operand is always determined with respect to the updated PC. The distance between the updated PC and our operand is referred to as an offset. When a program is assembled, this offset is placed in the first word location that follows the instruction. Hence, with relative addressing, the location of an operand is offset relative to the current value stored in the PC. If the instruction is relocated, the operand is moved by the same amount. Here's how we would write an increment instruction that involves the relative addressing mode. The symbol A is a label. It identifies the location of the operand that we wish to increment. That wraps up our discussion of the relative addressing mode. For additional information on relative versus absolute addressing, refer to the review section of your workbook. The relative deferred mode is the last of these special addressing modes. To explain how the relative deferred mode works, let's first compare it to the relative addressing mode that we just covered. With relative addressing, the CPU retrieves an offset value which is stored in the first location following the instruction. The CPU then adds this offset to the contents of the updated PC. The sum of the offset and the updated PC is an effective address that directs the CPU to the desired operand. Now, let's compare this to the relative deferred mode. Here again, the CPU adds an offset value to the contents of its updated PC. However, the sum does not represent the effective address of an operand. Instead, the sum of the offset and updated PC is used as a pointer to an address. The CPU first uses this pointer to locate the address, then it uses the address to retrieve the operand. Here we've placed the relative and relative deferred modes side by side. Note that the relative deferred mode, shown at the right, involves one additional level of addressing in order to retrieve the operand. Otherwise, these two special PC addressing modes are identical. As we've already noted, to specify relative addressing, we use the notation shown at the top. In this case, the symbol A is a label that identifies the location of the operand that we wish to decrement. To specify relative deferred addressing, we use the notation shown at the right. The @ symbol denotes we're using a deferred form of addressing. Consequently, the symbol A is a label that identifies the location where the address of the operand is stored. We've now described each of the 4 special PC addressing modes: immediate, absolute, relative, and lastly, relative deferred. Before going on to your workbook, let's quickly review the function of each PC mode. The immediate mode is equivalent to auto increment mode 2, except that it's used in combination with register 7. When an instruction specifies this PC mode, the operand appears in the first word location following the instruction. Thus, the first time the PC is incremented, it addresses the operand. Then the PC is auto-incremented to PC plus 4, so it addresses the next instruction in the program. This notation is used whenever we're calling for the immediate mode. Here, the number 100 is the operand that we wish to increment. Remember, this operand is stored in the first location following the instruction. The absolute mode was the second PC addressing mode that we covered. When this mode is used, an address is placed in the first location following the instruction. After the PC is updated to PC plus 2, it directs the processor to this address. The address is then used to retrieve the operand. Meanwhile, the PC is auto-incremented to PC plus 4. The value PC plus 4 is the address of the next instruction in our program. We use this notation to designate that we're using the absolute mode. Here, the value 1000 is the absolute address of the operand that we wish to increment. By the way, if the @ symbol were removed from this instruction, The value 1000 would be interpreted as our operand rather than the address of the operand. The third PC mode that we covered was the relative addressing mode. When this mode is used, it's necessary to calculate the address of our operand. In other words, the address is produced by adding an offset to the contents of the updated PC. The sum then represents the effective address of our operand. With this relative addressing mode, the location of our operand is always determined in relation to the updated PC. That's why we call this relative addressing. As we've indicated here, the relative distance between the operand and the updated PC is referred to as an offset. This offset is always placed in the first word location following the instruction. Now let's review the last of our 4 PC modes. The relative deferred mode is very similar to the relative mode. Once again, the offset is added to the contents of the updated PC. However, their sum is used as a pointer to an address. This address then redirects the CPU to the operand. Here we have 2 decrement instructions. The instruction at the left calls for the relative mode. In this case, the letter A is a label that identifies the location or relative address of our operand. The instruction at the right calls for the relative deferred mode. Notice the @ symbol. This symbol designates that we're using the deferred form of relative addressing. Consequently, the letter A is interpreted as a label that identifies the location where the address of the operand is stored. That concludes our discussion of PDP-11 addressing modes. We'd now like you to complete Part B of the exercises contained in your workbook. When you've completed these exercises, then take the self-scoring test, which is also included in your workbook. After you hear the next tone, turn off this playback unit and complete the workbook exercises and self-scoring test.